This stuff is not in the book. Not in the book. I might help if I actually plugged it in. Not in the book.
Phase change diagrams. Now, we all know that when you go over the mountains, what happens to the boiling temperature? It goes down. Things don't boil as hot. Now, when we say that water boils at 100 degrees Celsius, water freezes at 100 degrees Celsius, that is at sea level pressure. 1 atmosphere of pressure, which is normal sea level air pressure. As pressure and temperature changes, so do the melting and freezing points. And so we have what's called a pressure-temperature diagram. And we're going to make two of them. One for water and one for everything else. This is the one for everything else. Because water is unique. As we said, water is unique so many ways. Water is such a unique substance with all these qualities. I mean, if you had one or two of these qualities in a couple of different things is one thing, but the fact that water has all these unique qualities, you know, makes it just that amazing stuff. Now, these pressure temperature diagrams all kind of look like this. Now, this line, this is the line that's different for water. Now, for everything else, notice it goes up and to the right. It goes up and to the right. And what this does is the pressure and temperature combinations, what state will that substance be in? If you're in this region here, you're going to be a solid. So like for plastic, at 1 atmosphere, at 68 degrees for 70 degrees Fahrenheit, it's a solid. You know, that's if we have pressure temperature diagram for our plastic here. If it was in this region, it's going to be a liquid. Here is a gas. The lines represent phase change. These are the phase change points. So you actually have both together. When you're on the line, like here, you're going to have the solid and liquid. This is our melt and freeze line. Here is sublimation. Boil, condense. So you melt this line here, you're going to melt and freeze. This line is that sublimation line. Remember, we go straight from a solid to a gas. Carbon dioxide at 1 atmosphere pressure will go from a solid to a gas. In order to get carbon dioxide to a liquid, you'd have to have a much higher pressure on that. Boil and freezing. But it also means this. If I took a gas and I put that gas under pressure, even at a certain temperature, if I keep putting on pressure, eventually it's going to turn into a liquid. And if I put that liquid under pressure, it'll eventually turn into a solid. If you shake this, this is propane, which is a gas at room temperature. If I let it leak out of here, it'd be a gas. But you can feel the liquid in here, because it's under pressure. It's liquid, and if you listen, you can actually hear some of it's actually solid. There's solid propane in here on that. So pass that around, just shake it, you can feel the liquid as it sloshes around in there, and you can hear the solid in there pinging around in there. So just pass that around, don't drop it. Well, dropping it could always puncture it, you know, it's... Usually Mythbusters did things like that, not a lot. They shot a propane tank, didn't do a whole lot. The movie thing, you shoot the propane tank, it blows up, doesn't happen. Yeah, there really is nothing to ignite. Alright, now water. Water. Now you should put down, we have another diagram for water, because water is different. Now water, these two lines are the same for water. Water will act like anything else. If I take gaseous water and I put it under pressure, it's going to become a liquid. But the difference comes in this third line. It goes up and to the left. So we have our solid, liquid, and gas regions. So what's like it here? Well, we use it. So at 1 atmosphere of pressure, sea level pressure, I come across and I look, okay, water is going to melt and freeze at 0 degrees, and it's going to boil and condense at 100 degrees. That's kind of how we use this diagram. If I went to the mountains at a lower pressure, notice my boiling point is lower. The boiling point when pressure goes down is lower. But notice it's something else that people don't consider. Notice where is my melting point. The melting freezing point in the mountains is actually higher. Water freezes at a higher temperature in Lake Tahoe than it does here. Here is 32 degrees, 0 degrees Celsius. In Lake Tahoe, it might be 1 or 2 degrees Celsius that it freezes at. So pressure makes a difference. Pressure makes a difference on that. Also notice, if I have a gaseous water, and I put it under pressure, it turns into a liquid like all other substances. Like I said, the sublimation line and the melting freezing line, it works the same way for water. But if I continue putting liquid water under pressure, will it ever turn into a solid? No, which is a good thing because the bottom of the ocean is under extreme pressures. If water turned into a solid at very high pressures, the bottoms of the ocean would be all frozen. Again, if water was like all of the substances, a good portion of our oceans would be frozen solid. Wouldn't be liquid 5 miles down below when you get down to Challenger Deep. Enormous pressures, yes.
3 things. What does it say next to pressure?
Where are you looking? Pressure, temperature? Oh, 1 atmosphere, 1 ATM.
Okay, and then what about the both green ones?
Melt higher, boil lower. Melt higher, boil lower. Yes, ma'am. The red line would represent where this would be 1 atmosphere. This might be at sea level. If we were at a certain, in other words, it would tell us at sea level, if I'm at a certain temperature, what is the state of water going to be in? In other words, and where it crosses the lines, and this is true for any substance, where it crosses the lines tells us where it's going to boil, where it's going to freeze, where it's going to melt, etc. But notice, if you have solid water, and you put it under pressure, if you put it under solid water enough pressure, it becomes a liquid. And that's that regelation process. The water is unique. Water is the only thing that does that. Water is the only thing that does that. Okay? All other substances, when you put a solid under pressure, it just becomes more solid. But again, unique property of water. Water floats so the oceans don't freeze up. Water doesn't become a solid at high pressures. The oceans don't freeze up. I mean, if water became high pressure, Lake Tahoe, a good portion of Lake Tahoe would be frozen underwater. Because pressure goes up 1 atmosphere. Every 30 feet you go down, the pressure goes up 1 atmosphere. Okay, so you go down 300 feet, you're at 10 atmospheres. The pressure on you would be 10 times what it is right now. That's only 100 feet. Well, actually, you don't feel it, at 300 feet. Yeah, you don't really feel it. I mean, 10 atmospheres you wouldn't really feel. People can go to 300 feet. 300 feet is our limit for scuba because air becomes poisonous at 300 feet. The oxygen in the air becomes poisonous at that pressure on that. Well, you have to use weird things. Now, if you get much deeper, eventually there's a point where it's get crushed. But if the pressure inside and the outside, why is ships intact at the bottom of the ocean? Well, basically because it fills up with water, so the pressure on the inside of the ship is the same as the outside of the ship, so it doesn't get crushed. Unlike a submarine, when the submarine sinks, it's like air on the inside and water on the outside eventually gets to a point that it gets crushed. It's they call that crush depth. It's okay, there's the depth we can operate at, then there's the depth that we will become pancaked at. which is long before you get to the bottom. Alright, so one thing I want to add to this one, it's this point right here in the middle. It's called the triple point. Remember we mentioned the triple point back when we talked about temperature scales. This is the point that all phases are present. Usually on these lines you only have two phases, solid, liquid, liquid, gas, get solid, gas. At the triple point, all three phases are present at the same time. They're going back and forth. So phase change is occurring with all three rather than just two at the triple point.
Is that just for the everything else?
No, that's also true for water too. The intersection point, but I'm just pointing out the intersection. We kind of put all these labels on this graph. That's why I put it here. But it works for the water graph too. Because remember we said that the triple point of water is like 243 Kelvin at some very low pressure on that. So the last thing is retulation. Solid water turns to liquid under pressure. Basically, if I put this wire at the top of this big block, the wire puts a pressure on the ice, and it causes the water to melt. Well, can the liquid water support the wire? No, so the wire basically falls through, and then the water freezes, and then the ice underneath will melt, falls through, refreezes above it. So that keeps happening over and over again until this wire would go all the way through. There is a misconception that this is how ice skates work. Ice skates do not work by retulation. Yes, ice skates have an edge on them, but they do not cause retulation. Alright, this is not how ice skates work. Ice, if you go to the ice rink, on top of the ice is a microscopic layer of liquid water. You cannot see it, but it is there. And that acts like lubrication. That's what makes the ice slippery, is this microscopic layer of water on top of the ice. And it gets really, really slippery because if you need ice skates to skate, if you walked on ice with your street shoes, would it be slippery? No. Is ice slippery when you walk on your street shoes? Yeah? Believe me, when I was at school in college, I was always good to fall at least twice a year in the ice, slip and fall. The most memorable one, middle of the courtyard, it's all brick, black ice. So you couldn't see the ice. It was there, but you couldn't see it. 1 foot of the brick, whoosh, fell, all my books went off in different directions. Radiated away from me. I slipped one time, slipped and fell. A buddy of mine who was in my company, he was also from California, he came up, and remember why, it's like, I'm not going to laugh at you because he said, the minute I laugh at you, I'm going to slip and fall too. Kind of a California thing, it's like, we don't like ice. We didn't like snow, we didn't like ice, because, let's face it, snow is something you visit and then you come home. You don't live in snow and ice. I mean, that's just nuts. Alright, questions? Okay, this is it for chapter 23. So, homework tonight is your lab reports. Remember, if Monday morning they are in Google Docs, I'll do that. You guys can work on your calculations now. This is your time to work your calculations. You got 20 minutes. You probably have all your calculations done here by the end.